Hello everyone, and welcome back to the podcast. Today is Monday, June 8th, 2026. I am your host, Itano, and I am so excited to dive into today's trending article from the archive. I always love exploring these complex machine learning papers with all of you. We are going to learn something amazing today, just like we do in a bright and happy classroom. So let's all take our seats, open our minds, and get ready to explore the fascinating world of artificial intelligence. The paper you're looking at today has quite a long and fancy title. The title is Second Order Path Kernel Formulas in Machine Learning, and the current rule is ARC/ABS/2606.07495V1. Wow, it is long, right? But do not let the big words scare you, because we are going to break it down step by step together. So let us start with the big problem this paper is trying to solve. In modern deep learning, we train these massive neural networks with huge amounts of data, but one of the biggest mysteries is understanding exactly how the training data shapes the final predictions of the model. Imagine you are teaching a puppy to sit, roll over, and fetch. When the puppy finally learns to fetch, you might wonder which specific treat or which specific training session made the puppy finally understand. In machine learning, you want language training examples cause the AI to make a specific decision. Back in 2020, a scientist named Pedro Domingos proposed a formula. He showed that a model trained by gradient descent acts like it is comparing the test data to the training data. This is called a first-order path kernel. But right there is a catch here. That formula only looked at the surface level, or what they call the first-order geometry. It is kind of like trying to understand a roller coaster by only looking at the flat parts of the track. This paper, written by Jean Guo and Jean Mitchell-Morel, takes things to the next level. It develops second-order forms of these interpolation formulas. They are looking at the curves, the dips, and the bumps in the roller coaster track. In mathematical terms, they are looking at the curvature of the loss landscape. They show that the way the training sample affects a prediction is actually weighted by this curvature. And when you use stochastic gradient descent, which is how we usually train AI in small batches, things get even more interesting. A new component appears that connects the noise from these small batches with the curvature of the prediction. Let us delve deeper into this, because it is super important. The researchers proved that the curvature of the loss function plays a direct role in the prediction. It is not just about the model sliding down a hill to find the lowest error. The shape of that hill directly changes how much weight each training example is given. And for stochastic methods, they found that sampling noise, which comes from looking at only a few examples at a time, interacts with the curvature. If you use a very small batch size, the noise is louder, and it pushes the model to find flatter, safer areas in the landscape. Now, how does this compare to other technologies? Well, the traditional way to understand deep learning is to just treat it as a black box. You put data in, and you get answers out without knowing why. Other methods, like the neurotendon kernel, try to explain it by pretending the network is infinitely wide and never changes during training. But real networks do change, and their geometry evolves. This second-order path kernel technology is much more advanced. It compares the model not just at the start but all along the training journey, and it factors in the twists and turns of the training path. It is a much more realistic and detailed map of the AI brain than we've ever had before. I promise to give you some specific examples of how this applies to everyday life. Let us talk about 3 real-world applications based on this amazing research. First, think about artificial intelligence used in medical diagnosis. Let us say an AI is looking at X-ray images to find signs of illness. If the AI makes a diagnosis, doctors need to know exactly why it made that choice. Using these second-order path kernel formulas, we could trace the AI decision back to the specific training images it learned from. Because this formula accounts for the curvature and the batch noise, the explanation would be highly accurate. The doctors could see that the AI is relying on the right features, rather than just random noise in the background of the image. Second, let us imagine autonomous driving systems, like self-driving cars. These cars are trained on millions of miles of driving footage. Sometimes, a car might make a sudden, weird decision because of one unusual training example, like a person in a dinosaur costume crossing the street. By understanding the second-order geometry, engineers can see how sensitive the car brain is to these rare events. They can adjust the batch sizes during training to make sure the car finds a flat, stable minimum. This means the car will drive smoothly and safely. without overreacting to strange sights. Third, consider the personalized recommendation systems on your favorite video streaming apps. You know, the ones that suggest what movie you should watch next. Sometimes they suggest something completely random, and you wonder how they came up with it. With this new mathematical understanding, and engineers to precisely calculate how your past clicks influence today's recommendation. And they could use the curvature-weighted formulas to filter out the noise of accidental clicks. This would lead to a much smarter, much thorough recommendation system that truly understands what you want to watch. So class, what have we learned today? We have learned that training an AI is not just about drawing a straight line from start to finish. It is a bumpy, curvy journey. And by using second-order math to understand those curves, we can make AI safer, smarter, and much easier to understand. The researchers even did experiments to prove that smaller batch sizes make the model output more stable, which completely matches their formulas. It is just so wonderful to see math and computer science working together to solve these big mysteries. I hope you all enjoyed this deep dive into the archive as much as I did. Thank you so much for listening today, and I will see you all next time for another fun adventure in learning. Have a great Monday, everyone.